All right, so we have the spectral theorem in the box. This rather amazing result here. Whoop. Pretty fantastic. Symmetric matrices, real, can be decomposed or factorized in this way, where we have a very delicious diagonal matrix with the eigenvalues sitting on the main diagonal. And then the eigenvectors normally would be an S here to the Q because it's an orthogonal matrix. And this would normally be an S to the -1, just the transpose. Pretty spectacular. So just a couple of pages here to argue about why all of this works. Not complete, but we'll get some of it done properly. Okay, so the entries in A are real. We're assuming that. All right, so there are these pieces. All right, so this is going to be number 1. So we're going to show that all of the eigenvalues are real, which basically means no rotation. Right, it's just a stretchy matrix, but flips and stretches, maybe some squeezing. Okay, so we assume we have these two facts about our matrix, right? It's symmetric, and the entries are real. All right, so let's just take an example eigenvector, eigenvalue here, right? Situation, and we're going to test to see if it can be complex. So this is a little bit outside of our box, but that's okay. A complex number, right? So it's a real number plus a real number times the square root of -1, which we write as I. Yes. And we're interested to see if, you know, this is a b not equal 0 case. So, right, rotations are here if that's a complex piece. So there's a little bit outside of what we're doing, but it should be something you know about. So complex conjugate, we'll put an overbar over a number. So complex conjugate of a plus bi is this special thing where we just flip the sign of the imaginary part, right? The bit that's multiplying the square root of -1. So an important thing to know is that, right, and there's a little result. If we have two complex numbers, we take their product, then the complex conjugate, then that is the same as taking their complex conjugates and multiplying them together. Don't have to worry about it too much, but we're going to use it. So we'll just use these things, we'll argue through. So we've got this truth to start with, right? Just an eigenvalue equation, right? Square matrix. Yeah, so square matrix, it's n by n times a vector equals a number times a vector, same vector. So we're going to go in two directions here, right? Down here and down here. So let's go off to the right to start with. And maybe so we're going to take complex conjugate of both sides. So we'll do this, right? That's what these overbars are. A is real, so that disappears. We're going to just leave these ones here. Right? A is filled with real numbers. We're going to take the transpose. So this one swaps. Maybe I'll use this. Right, so we swap to here. V transpose, A transpose is here. We're trying to use the transpose aspect. Lambda is just a number, so it doesn't, and we just take the transpose here. Okay, so these are still an overbar here, overbar here, overbar here. Now we have, now we use the fact that it's symmetric. So we've used both of our pieces here. The numbers, the entries are real, and it's symmetric, so the transpose vanishes. Okay, all right. So this is definitely monks, right? So the monks are helping us with this. There are some monks that went other ways, and we never heard from them again. And then the monks tell us to also go in this direction because something good will happen. And so we're just going to, so we're going to take the original equation and pre-multiply by V transpose. That's what this statement is here. And we pre-multiply here by V transpose. Right. And over here, we're going to post-multiply by V bar. So this is still a complex conjugate. This is still a complex conjugate. And we're missing a few bits over here. So this should be V transpose V And there should be this bar on top. Okay. So the right-hand sides look the same, right? So this matches, and this matches. So we've taken two roots to get to the same place. The only thing that's different is lambda and lambda bar. So we see everything matches except this. So we have to have lambda as lambda bar. So lambda is real, right? The complex conjugate of a number is real. It means it has no imaginary part. That is the argument here, right? To get this first result. Okay, good, exciting. We're not going to have a complete argument for the second part, this rather surprising thing that the eigenvectors are orthogonal, but I think we'll get the intuition. That's okay for now. All right, so this is a second piece. So the A's eigenvectors form an orthogonal basis, which can be made orthonormal for Rn, right? This is why we can write Q and Q transpose. Big deal. I mean, this is really, really cray. So again, we have that the A is symmetric and that it has real entries, and we want to show this, right? So this is our game now. Let's turn it into a matrix thing. So we want to show that this is true. Every pair of eigenvectors, if we take the inner products, then they are. This is supposed to be the vector. The vectors are at right angles. The inner products give us 0. Right. So we'll do this just for a little bit, and we'll work up to a sort of a full story. So we know that if for normal matrices, if the eigenvalues are distinct, then we have an independent, linearly independent set of eigenvectors. So that was a start. So let's see what happens when we know this extra piece that A is A transpose. That's really what we'll use as the transpose part. So again, it's this kind of taking two different paths and using transposes and so on. This is this is an interesting construction, right? What does this thing look like? We'll see a little more of these in the remainder of the course. So this is a vector, matrix, vector. So this is in fact just a number, right? So this is a 1 by n because it's the transpose, n by n, and an n by 1. So this whole thing is just a number. Right? Matrix times a vector gives us a vector, and then it's an inner product. All right. So we've got some number, and we can play with it in two different ways. One is to cordon off. So we'll go this way first. We'll cordon off the AV2, and we'll use the fact that it's an eigenvector. So we're going to replace it with lambda 2 times V2. And we can pull that lambda, we'll extrude mathematically, we'll extrude it out the front. And then we just have lambda 2 times this inner product of V1 and V2. Right, so this is what we're after. We're kind of after this. Yeah, that's what we want. What we're interested in. So that was sneaky. And yeah, this is 1 and 2. Obviously, it could be I and J. That's no problem. We could, so there's a transpose here. We could cordon these things off in this direction. So we'll do that this way, right? So we could actually, look at this goodness, right? So this would undo itself. So A transpose would be this piece, right? Using the transpose rule, and V1 transpose would be on the left. Now, A transpose, so this is, A transpose is, right? A transpose equals A. And then A times V1 is just lambda 1 times V1. So we end up with lambda 1, and we have this same blob, V1 transpose V2. So these are all equal to each other. We've started at the same place and moved in two different directions, so these have to be equal. But we assume that lambda 1 and lambda 2 are not equal to each other. So the only way they can be the same is if this is 0. They're both 0. Right? Because they're multiplying the same quantity here. So it's lambda 2 times blob, lambda 1 times the same blob. That blob has to be 0. So that's the end of that little story. So that's only if, so if we have two eigenvalues that are different, then their eigenvectors are at right angles to each other. So the question now becomes, what if you have eigenvalue, if you have an eigenvalue that's repeated 3 times, how do we know we get enough eigenvectors associated with that? All right, so that's this concern. What if an eigenvalue is repeated? Right, we're worried about this. Right, we're worried we don't get enough, we won't have enough eigenvectors. This is this problem, we can have deficient matrices. But we know this thing, we know that it's a symmetric matrix. And it turns out symmetric matrices are pretty great. So, just going to work through these 2 examples. Obviously, this isn't a general proof, but just 2 examples to give you a sense of how things must work out. So this is, right, so not symmetric and symmetric. So let me write that. Right, so this is not symmetric, is on the left-hand side, and then symmetric. And see how they behave as we kind of mess around with them a little bit. So if you go through and find their eigenvalues and eigenvectors, on the left we have repeated, and on the right we have repeated, right? So repeated. So it's the kind of thing we're concerned about. But when you go and find the eigenvectors associated with, we find only one here. There's only one dimension eigenspace, but we find 2. 2D eigenspace. Right, so this is healthy, and this one is sad over here. There's some sadness. Okay, well, let's do something here. How can we see that because this is symmetric, it's going to be okay? Of course, it's just the identity matrix. So we'll do this sneaky little thing where we'll just add, we're just going to add a little piece here. We're going to add an epsilon here and an epsilon here. And see what happens as we move away from being, as we move away from having repeated eigenvalues, or think of it this way, as we move 2 eigenvalues towards each other. So we sort of slowly move them towards each other. So now we have distinct eigenvalues, right? So these are now distinct. Right, and these are distinct as well. Okay, that's good. Okay, so we want to highlight this. These things are distinct. These ones are distinct, right? 1, epsilon is greater than 0. We're going to let it go to 0, but epsilon is greater than 0. If you go through and find the eigenvectors, and we know that if we have distinct eigenvalues, doesn't matter if it's symmetric or not, everything's okay. So this is okay, right? So we end up with 2 eigenvectors that are different. But, okay, and these ones are fine too. And these are the same as before. So this is as before. So as epsilon goes to 0, let epsilon go to 0. That's the statement here. All right. Right. As epsilon goes through, we see the eigenvectors become the same, right? So this one will go to 1, 0, which is the same as this one. They collapse. These ones don't collapse, though. For all epsilon, they're 1, 0, and 0, 1. They're not going to collapse. They're at right angles to each other. So they don't budge, even though the eigenvalues come together. So this is generally the story, right? So symmetric matrices, we could take one and add a little bit. We could move the eigenvalues all a little bit, make them distinct. Suddenly, like just add a tiny little bit so that these eigenvalues that were exactly the same are now just differ by the smallest amount, very small amount. And then suddenly the eigenvectors for those will be at right angles. Right? That's what we showed on this previous page, right? If they have different eigenvalues, then the corresponding eigenvectors will be distinct. So that snapping doesn't make sense, right? This is kind of this should be a smooth thing. The eigenvectors should move around smoothly. So it means that as you move 2 eigenvalues together, so that eventually they're the same, for a symmetric matrix, they will stay at right angles the whole time. They can't snap closed. And that's what this picture is showing here. So this is the one of the eigenvectors 1, 0, and the 1 epsilon 1 is collapsing down, right? It's collapsing down. But this is not happening for all epsilon over here. It's staying stuck, and they can't just go. So that's what this statement makes. Requires requires more work to do this. Work to show in general, but we have the basic idea. Basic story here. All right, so that tells us why these things work, gives us a good sense of why these things work. But yeah, pretty spectacular thing. So any square matrix that's symmetric and real can be diagonalized such that you are guaranteed to have an orthogonal set of eigenvectors, real eigenvalues, and the diagonalization is, so it might be hard to get to the eigenvector, but once you've got them, Q transpose is easy to produce. That's the, right, so it's going to be Q capital lambda Q transpose, which is really S inverse, easy to do. So this is a beautiful story, and even better is we can write it out as this sum of projection operators. So we will see a little bit more of that soon with singular value decomposition, but this is a great place to end the eigenvalue story. Okay.